on now. So this will be recorded so that others who aren't able to watch it live can watch later. It'll be posted on the PICUP website. Just a etiquette note, if you're not, once we get into the meeting, if you're not using your microphone yourself, that just helps on the audio quality for everybody.
Wait. I'm sorry. So you say to mute? To
Yes.
mute if we're not talking? Is that what you just said? Okay.
So a couple other announcements. So our next synchronous meeting is currently scheduled for Wednesday, October 23rd at 4 p.m. Pacific. And we are looking for volunteers to either present something they've been working on, either an exercise set or something they've been working on in a class or something in their department, or to lead a discussion. So if you're interested, please let me know. And then the other announcement is that the committee that we have that organizes these things, which is myself and a few other brave souls, is looking for more volunteers. So if you're interested in actually helping to organize these things, again, please let me know. Okay, and with that, I will turn it over to Walter, who's going to talk to us about his nonlinear vibrations exercise set.
All right, so this is the capstone project for Physics 307, which is a computational physics class taught at Syracuse. Can everybody hear me okay? Okay, so this is the capstone project. This class is intended for students who are dedicated to studying computational science, but not necessarily physics majors. We don't assume any prerequisites other than taking Physics 1 and taking calculus. So we've had students take it straight out of intro physics for engineers, but we've also had students from diverse majors, like we had an architecture major, we had a music major who was one of the best students we ever had. We had a bunch of physics majors, a bunch of computer engineers, people like that. So we get a diverse mix of people who have, most of the students are either people who have computing skills and find the idea of simulation as an interesting thing to add onto their CS resume, or people who are physics majors who want to learn computer simulations. And my goal in designing this assignment was the standard lore that, you know, the PICUP message that everybody's probably kind of internalized now is that computational physics lets us teach physics better. But I think it's worth kind of unpacking that, picking at it and seeing what it means. It means, yes, that we can use computation to teach the students the same stuff we were already going to teach them, but teach it to them in a more efficient, deeper way. But computational physics also lets us teach students things that they would be unable to understand at that point in their career totally. It let us completely reshuffle the curriculum. And so I've presented this before, and the subtitle of this exercise set is really Perturbation Theory for Sophomores. Because the point of doing this exercise is to, you know, I was thinking, okay, in a computational physics class, we want to choose physical systems to simulate that let us teach computational science, but also along the way, we want students to get insight into physics. So most of my students have not taken quantum mechanics yet, but they will. So this exercise set was designed to prepare them for things like the 1D oscillator by helping them understand issues like normal modes, but also to go a little beyond and to dive into some perturbation theory. So let me actually start with a quiz. So I'm going to share my screen with you. Let me figure out what button I have to hit to do this. And so here I am going to show you, so this is a computer simulation, this will come up, of many strings vibrating all at once. Now I don't have the students simulate lots of these at the same time. I'm just doing this for the purposes of this demonstration. So I'll ask you, let me change something here. We'll go down to the first normal mode. So the way these simulations are constructed is each of these spheres is a point mass. Each of these lines is
I'm sorry, Walter. Should I be seeing something besides you right now? Because I'm only seeing you.
Oh. Oh, sorry, there was a question of select what you want to share. Now you should be seeing something, do you?
I am. Thank you.
Okay, sorry about that. Thank you for, oh, but now I have to try to get these windows out of my face. Here we are. So let me restart now. Oh, I'll make this go very slowly. So the basic model that we're simulating is a collection of point masses connected by Hooke's law springs. These Hooke's law springs are ideal in that they are perfectly linear, but they do not have zero equilibrium distance. So a lot of students will say Hooke's law says F equals minus kx, but it's really F equals minus k x minus x naught. So that said, we can model a guitar string like this. And all this is F equals ma done a lot of times. So I'll ask you this. Let me now increase the time step so this runs faster. So here is one simulation of a collection of vibrating strings. So this is simulation A. So the only thing that's different about these strings that I'm showing you is their amplitude. This one in the front is vibrating at a very high amplitude. The ones in the back are vibrating at a very low amplitude. But other than that, all of their parameters are the same. So here is one simulation. And now here is another simulation. Let this run for a bit. So what differences do people notice between them?
Looks like there's a phase difference.
Yeah, there's a phase difference.
Right.
And I haven't programmed in a phase difference. I started them all in phase. So if they started in phase and got out of phase, what do you conclude from that?
Could it be that you're in the computation of this, there's no longer a small angle approximation, small amplitude approximation, or?
Exactly. And this is something that the students, even the students who've taken their waves and vibrations class, they won't know. So when the professor does the derivation of, hey, if you have a vibrating string, it obeys the classical wave equation, there's always a small amplitude approximation in there that the students just forget about. Because in that class, the only thing they can ever do is the limit of small amplitude. But there's a whole lot of really rich phenomenology in the world of non-small amplitude that's accessible by the computer. So this project takes the students a couple of weeks, and they first start by investigating, so they construct a model. They have to do a lot of work to go from the macroscopic properties of a real guitar string that you might buy at the music store, its composition, which is its Young's modulus, its radius, its length, the tension that you put it under. They have to go through a lot of thinking to go from there to calculating the masses and spring constants of these little links and dots that make up our model. So they do that. And then the next thing that they do is explore all of the small amplitude behavior, all the normal mode stuff that I'm not going to go over here. That is, we all know. And then at the end, we look at the nonlinearities, and that's where all the rich phenomenology looks. It might be a little difficult to see. I'm trying to find a good angle, but look at the string with the very highest amplitude. Is it vibrating sinusoidally?
It's hard.
I really can't tell.
But it looks like it gets to a point where it's almost flat, where you can see the different modes on it. Like
So
more than one mode.
Yeah. So here I've gotten all the others out of the way. What's going on here?
I really can't tell. I mean, it looks. I mean, at this step size or whatever it is, it looks kind of okay to me. Oh no, wait. At the next to the highest amplitude, I see a flattening at the top of it.
Yeah, right. So So two things. Yes, that's absolutely what's going on. We started this in a sine wave, but the idea that that you can understand the behavior of a vibrating string as a collection of independent orthonormal linear normal modes is only valid in the small amplitude approximation. So we see coupling here between all of the different normal modes, as someone pointed out. This is n equals 1 coupling to n equals 3 and n equals 5. And if you look carefully, you can even see motion in the x direction. So there's coupling between the longitudinal and transverse modes, something that we don't think about. And all of this behavior happens very naturally in the computer model. I didn't do anything special to get this.
Can I just add
You just
one
went to
more
high amplitude. That's it?
Yes, that's all I did.
Huh.
The other simulation that I showed you, where you only saw linear behavior like this, I have a flag in my code just for demos that actually runs it at 10 to the minus 12 times the amplitude, and then magnifies the animation by 10 to the 12. So this is a trick, right? What you're seeing here, this linearized version, is a trick. This is the actual correct physics.
But it is neat that you can go back and forth, right? You can actually show them the small angle approximation, right? Or and you can kind of naturally move back and forth between the nonlinear behavior and then the linear behavior at small amplitudes.
Yes, and they can do it too. So let me go to even higher amplitude. Let me turn on the parallelism again, and you can see that this oh, sorry, wrong button. This one in the front, you're seeing a lot of non-sinusoidal things, but the ones behind it are well behaved. So this is a qualitative introduction to perturbation theory. It turns out if you push these too hard, you get into the nonlinear regime where you have an uncontrolled energy flow to n equals infinity. Like energy just spreads out up through all of the normal modes.
Well, I'm sorry, Walter, I don't get it. So perturbation theory is, as I normally do it, is you take something and then you add as a perturbation something else. But you didn't do that here. You simply solve the real equation.
Yes.
You didn't add a perturbation. So in what sense is this an introduction to perturbation theory?
Because it's through the back door. We don't actually have the students use perturbation theory to solve the system. What we do is we use the language of perturbation theory to understand our results. And let me show you what I mean. So one question that's interesting to ask is so this is all qualitative. Let's ask the quantitative question now. How does the frequency depend on the amplitude? Because as you saw, they got out of phase, so they have different frequencies. So what I'm going to do now is I'm going to run 20 of these. Let's see, let me pick a good range. So here are, oh, this is going fast enough, I can do more. Whoop, mistyping my parameters. So here are a lot of them. Oh, that's too slow, I'm sorry. Here are a lot of them running, and you'll notice that after they complete one period that my computer prints some numbers to the terminal. So you'll see some numbers appear here on the left, right there. And what those numbers are the amplitudes and the deviation from the period you expect in the linear case. So again, we're using perturbation theory not to solve the system, but to say that since this system is perturbative, the periods we expect are the small angle period plus a correction that's a power series in the amplitude, right? That's the idea of perturbation theory, that if your system is a power series around an ideal system, that your behavior will be a power series around the ideal behavior. So I'm going to run this again. And once this is completed one period, one half period, so once we've measured, excuse me, one full period, so we've measured the period of all of these strings, I'm going to plot those data. So we finished now. So plot mode1.txt lx amplitude. So I'm typing in axis labels now, so we're clear. Can all of you see the GNU plot window that just showed up? So this looks pretty weird. And our students actually work very hard to interpret this. They've seen something similar for the pendulum earlier, so they're not unfamiliar with this. So for high amplitude,
Larry,
oh,
I'm sorry. I'm sorry, Walter, can I interrupt? What's
Sure.
on the horizontal axis again? I can't
Amplitude.
see a label.
Amplitude.
Oh, amplitude on the horizontal axis. Okay, thank you.
Yeah, is it cut off on the screen share?
It is for me.
Okay. So for large amplitude, so amplitude bigger than about 2 times 10 to the minus 2, this is a straight line on a log-log plot. Well, what do straight lines on log-log plots mean?
Power law.
Power law.
Power law.
Exactly. So the students, we've been doing this, well, we will have been doing this all semester. I've taught this before. We're not here yet this semester. And the slope here is 2. So this means that the shift in the period is quadratic in the amplitude. Now, is this what you expect?
I would have no idea what to expect.
Right. So the idealization is small angle approximation, right? Where you replace sine theta with theta. But the next term in the power series for sine theta is 2 orders down in theta. It's theta minus theta cubed over 6. So since we're making a proportional error of theta squared in our small angle approximation, it shouldn't be a surprise that the shift in the period is quadratic in the amplitude, because that's the next term in the power series of sine theta. And this idea of power counting is crucial to, for instance, chiral perturbation theory for a lot of sort of fancy pants quantum field theory. But we're getting students used to this kind of thinking in terms of power series expansions and leading order and next to leading order and so on. So yeah, over here, this straight line is the effect we're looking for. What's going on over here on the left, right? Why do, even in the limit of very small amplitudes, why do we see a shift in the period?
Could it be the finite step size in your simulation?
Yeah, exactly. It's the fact that we didn't do a perfect job of simulating it. So yeah, that could be what it is. I happen to know that in the code that I just ran for you, I'm using the Leapfrog integrator here, which does a pretty good job at the step size I ran it at. Actually, what this is that I have a finite lattice spacing. Hi, Steve. I'm modeling an infinitely flexible guitar string as a series of linked points, and I have a finite number of them. And in fact, that discretization error is the leading error that doesn't depend on amplitude. And the students have to tease that apart, right? Tease apart why this part of the graph on the left looks like it does, why this part on the graph on the right looks like it does. And then you can understand this spike in the middle, which is just that those two things have opposite signs. And since this is a log-log plot, we took an absolute value.
So Walter, how many students do you have so that you can have them working and teasing this out and you can be working with them?
I usually have around 20 or 22 in the class, and I
Many.
hire, yeah, a lot, but I have really, really good undergrad learning assistants, and that's the key. My students find this class really exciting and compelling, and they always want a job teaching it next semester. So I have lots of help. So that's the project. I kind of gave you a whirlwind introduction to this. I have two things that we could do now. If you have any questions, I'd be happy to answer them. But I also have some data measured from a real guitar to convince you that this is not just something that's a numerical toy. Which would we like to talk about?
Well, so I'd love to see the data, but maybe while you're pulling that up, if anybody has any questions or comments, now's a great time to chime in.
I think this is beautiful. My question earlier about why is this perturbation theory, you answered very well. So at this point in their career, you said this is typically for sophomores. They don't know anything about perturbation theory. Do you somehow, at the end of this, point out that, well, normally when we do perturbation theory, we go in the opposite direction?
Yes, because this isn't their first taste of perturbation theory. We did this with the pendulum earlier in class. This is the fancy one at the end of the semester, but they've already seen a nonlinear oscillator and used this same analytical framework to understand that. The difference is, number one, guitars are cooler than pendula, and number two, the pendulum doesn't have a discretization error, but this one does. So now they have to think really hard about modeling. So modeling is kind of the last piece of the puzzle we get to in our class.
But I guess my question was, that's great, but my question was more that, like, when they eventually do get to perturbation theory, it's going to be from the totally opposite direction. So do you kind of prepare them so that when they get to, like, the usual implementation of perturbation theory, they're not massively confused?
Yes, we do.
Oh, good.
Yes, we do.
Good. That's great. This is beautiful. I love this.
Thank you. Any other questions or comments before I show you some data measured with a microphone?
So, hi, this is Sujata. I'm at University of Florida. We don't do any computation with our undergraduates, but I have a slight question about how much have the students done before they come to this exercise?
Before they come to this class, none. Before they come to this exercise, about 2/3 of a semester.
Thank you.
You may have noticed, by the way, on the top right of my screen, you may see Slack messages popping up. I have actually, my students in my class right now are Slack messaging code to the Slack channel. And if my learning assistants don't get to his question before this meeting is over, after the meeting, I may answer their question. So we have a very rapid feedback loop to help students. So his message is, hey, so is there anything wrong with this? My plot didn't turn out the way it should. So he's presumably going to send me a plot and have me look at it about an earlier project. Again, this project is not where they start. This is the capstone.
Oh, I had a very small technical question. So the plot that we're looking at right now is a GNU plot, and what you showed us earlier, I guess, was GNU plot. We never asked what language they're using when they're doing the simulation, number one, and number two. So that's the first question. What language are they using?
Half of them half of them Python, half of them C. I don't care. One of the things I emphasize in my class is that this is not a computer science class. This is not a programming class. I have notes that teach them both languages, and they can take their pick.
Okay, so you're agnostic. And then those who use Python, are they typically using matplotlib, and then those that are using C typically use GNU plot? Or do they both save their data to a file and use GNU plot? Or is it you absolutely don't care about that either?
I don't care. If they want to use matplotlib, they can, but I have a tool called plot. You may see it in my command line.
Your tool is fantastic, by the way. Yeah.
Oh, this guy? This thing?
Well, I thought you were going to talk about your
animator? No.
Animator, but
I can talk about it if you want. But plot. Oh, go ahead.
No, that's a big distraction. It's a great distraction, but it's a big distraction.
Yeah. It's pretty, but it's not the physics. Yeah, plot is a Perl front end to GNU plot, and that's what I have them use. I want them to get used to this idea of input and output redirection and working with text files on disk, because that's how real research groups share data. And I want to get them acclimated to the Linux command line. So that's a key learning objective.
Okay. So are most So are most of your students using this
Mhm.
plot and redirection? Okay.
Yeah.
Got it. Thank you.
Any other questions? Okay, so the data we're looking at, so here I've plotted the deviation, the fractional deviation in the period for both the first and the second normal mode, and you see that the second normal mode has more nonlinearity. It's what you'd expect because a power series in amplitude doesn't make any sense because that's not dimensionless. It has to be a power series in amplitude divided by wavelength. So if you look at the numbers, you'll see that the second normal mode has 4 times the nonlinearity of the first normal mode because its wavelength is half as much. And the nonlinearity goes as amplitude divided by wavelength squared. So it's really difficult to control amplitude on a real guitar well, and it's very difficult to select for a single normal mode. But what I did was I took an actual guitar and plucked it right at the end of the string, so it coupled very strongly to all of the normal modes. So I got a really tinny, pingy noise. I recorded it with a $20 microphone from Best Buy. I ran it through a Fourier-O-Matic, and I plotted, I think this is the plot I want. So what you're looking at here, let me put some axis labels on it. So what you're looking at on the x-axis is the normal mode number, actually measured off of a guitar. And on the y-axis is the nonlinearity in cents, which is a musician's unit of detuning. It's a very small amount. So these are percentages of a half step. So percentages of the distance from one piano key to the next. And so 2 cents is almost inaudible. And you see that in fact the nonlinearity, so all of these were recorded at the same time. So they're all on a string that's vibrating with the same amplitude. It turns out it's kind of the aggregate amplitude that matters. And so this was measured. And if you fit it to a quadratic, you get this, which fits almost perfectly. I mean, notice this is to fractions of like a small percentage of 1/12 of an octave. So, for a $20 microphone, that's not bad.
It's almost a commentary on how good your microphone is. Walter, make sure I understand what you did here. So you measured the sound coming from the guitar string.
Mm-hmm.
You pluck the guitar string near one of the frets so that you get as many of these different modes as possible.
Mm-hmm.
And then you took the Fourier transform and you divided those Fourier coefficients by the fundamental. Is that what that is? Is that what I'm looking at?
Not quite. So if you would expect, say, the 15th normal mode to have a frequency that's 15 times the fundamental, right?
Yeah.
So what you're seeing on the y-axis is the actual measured frequency of the 15th normal mode minus 15 times the frequency of the fundamental.
Oh,
so
I see. I get it. So it really is the nonlinearity part, right?
Yeah,
of course.
Yeah,
got
we've
it.
extracted the part we want.
Got it.
And I show the students these data. We don't have time to do this in class, although it would be cool. I just show these students these data, and I bring in a guitar and make the measurements in front of them. You can see it on a spectrogram. You can see basically if you pluck a string at very high amplitude, you can see the frequency actually slowly creep down as the amplitude decays. So I've talked a bunch about physics, but I want to call out something that happened here. We all got really interested in the physics, right? I was asking you all physics questions, and you're like, hey, I think it's this way. Hey, I think it's that way. Hey, why did it do this thing, right? We've kind of gotten invested in this physics story here, but the student-facing story is computational physics lets students who are fairly early career in learning physics learn things, access things, experiment on things that are interesting enough that a group full of PhDs is discussing them and finding them cool. And this, I think, is part of the real power of computation in the curriculum, is it gives early career students a very direct access to really fancy physics ideas. We've talked about power counting, which touches on a lot of quantum field theory. We've talked about perturbation theory and kind of doing it backwards, as you pointed out. We've talked about nonlinear acoustics, which my musician colleagues actually don't know. They know this effect happens, but they don't know why it is. We've talked about, data visualization, interpretation, a whole lot of computational science, and things that we find interesting, but sophomores and juniors can do. And they find that really compelling. They find the fact that they can get their mitts in stuff that all of the PhD folks are still finding interesting to be a really compelling part of the course.
Well, great. Thank you so much, Walter. And any last questions for Walter before we move on?
I don't have any more questions. I've asked a lot, but I just want to say this is fantastic. I guess I do have a question though. Are you going to put this into the PICUP site as a lesson or exercise, or?
It's already there.
It's already there. Terrific. I'll dig it up. This is great.
There is a link to it in the chat window, which you can get there on the bottom of your screen. There's an option to open up the chat window. Okay, well, thank you so much, Walter. We'll give you a virtual round of applause. Ernie, we had you up next. We've got about 20 minutes left. Do you want to go ahead and present, or do we want to save you for another time?
I'm sorry if I ran over time.
It's not a problem, actually. My exercise set is very humble by comparison. So let me see if I can share. I'm getting a message that I cannot. Maybe now I can if Walter's not. Yeah, okay. So I've got some slides. And can everybody see the slides? Or holler if you cannot. How's that?
Yes, we can see them.
Yeah.
Okay, great. Okay. So I'm talking about the Rainbows CES that's already up there and on the PICUP site. And so this should be relatively quick because the computation is really very simple, but the physics, I think, is worth it. And I think I would also like to comment on including it in the upper level. There's a lot of background, especially for people who are just getting started. I think you have a lot of questions, and hopefully I'll address those. Okay, so first I want to set a little bit of scale here of where I'm from. I'm from Eastern Michigan University. We have about 15,000 undergrads, bachelor's and master's program. You can see what our building looked like in November 2017. It looked like a parking garage. They had completely gutted it, and we were scattered across campus, and now we're in a fully renovated building with a nice looking optics lab. So the outline for what I'm going to talk about, I'm going to start with my end message, then talk about the Rainbow set, and then talk about specifically how I implement it. And hopefully that'll get at some of the questions that anybody who's sort of new to this can benefit from. Okay, so let me begin with the end. Okay, you're all here, so you probably agree that computational physics needs to be integrated with our programs. And for those of you who are new to this, welcome. And also I'd like to point out that there are 3 reports that you really need to at least read the executive summaries of, which is just a few pages each. It's the JTEP report from the Joint Task Force for Undergraduate Physics Programs from APT and APS, which talk about skills and knowledge that physics majors should have when they finish their undergraduate. There's a report on computational physics from the Undergraduate Curriculum Task Force from AAPT that I helped lead. And then there's also a laboratory recommendations from the APT, which also has a lot of overlapping goals. So I think something that Walter touched on is that you can do things better by teaching computation within a physics context. I'd say you can also accelerate lab learning too by making sure students have good computational skills. Okay, that's the purpose of this whole meetup was getting at intermediate physics. And the bottom line is that there's no question that interesting content beyond intro physics is more time consuming. There's a lot more detail and something is going to have to give. And so my bottom line is that what has to give is maybe your expectations about how much coding your students can handle. So you really need to know your students and know what their prep is. And my experience in my context, my school, is that the students actually need quite a bit of support. Okay, swinging into the rainbows exercise set. If you go to the exercise set tab on the PICUP website and click on waves and optics to do a search, you'll see a couple of my exercise sets actually happen to pop up right away. And the second one is rainbows, easy to find. Okay, and my motivation for doing it, of course, is that it's an inspiring natural phenomenon and it can trigger computation at different levels of sophistication. And you can actually use it in the classroom or the laboratory in different levels as well. What I've shown here is a screenshot of a, I guess I would say, infamous YouTube video of someone in the Yosemite Valley in California who woke up, found a double rainbow outside his window and had a tremendous emotional response to it. If you have never seen this video, I highly recommend that you take a look at this video. Okay, so swinging in, what do we actually do in the computational exercise set? We basically get the students to read enough of a peer-reviewed paper to actually extract refractive index versus wavelength for water and for air and to make them plot it. This actually helps students to realize that they really can do this, and it's something they may not have really done much of or any of prior to doing this work. The second thing is that they derive an expression for the deflection function, which is really pretty simple geometric optics, and then actually plot the deflection function versus incident angle on the raindrop for different wavelengths, because now they can do this because they've already figured out refractive index versus wavelength. Then they can figure out the angular positions of the colored bands of the rainbow, and so far you're saying to yourself, this is all basically introductory physics, and I would probably agree with you, although the students may not have done all of this work of actually being careful about refractive index. But the more advanced or intermediate part is actually to answer the question why the rainbow is bright. Not where it appears in the sky, but actually why is it bright? And that's the intermediate piece. Okay. So swinging into this, so here's a plot that they basically generate. This is done in Python. It could easily be done in Excel. So if you are just starting out and you're not comfortable with Python, you can do this stuff in Excel without any problem, I'd say. But we do it in Python. And I should back up the truck slightly and say that at our school, we have implemented 2 computational physics courses that are required for our majors. One is a 1-credit introduction to Excel and Python, and then there's a second 3-credit-hour course, which is computational physics using Python. So it's more like Walter's 307 course. Okay, so one of the first tasks is just making sure that they can read a paper, extract what they need to plot a function, and plot a function. They do the same thing for the index of refraction of air, again, versus wavelength.
Ernie, can I ask a question real quick on that? So
yeah.
Do you suggest papers, or they just Google, or?
Oh, no, I suggest. I definitely suggest. Okay. I mean, I suppose that we could let them loose, but I'm much more targeted because, as you'll see, the context in which I have them do this is pretty structured. And I think that that helps a great deal because even with our students having taken the courses, they still don't feel fully comfortable. they need practice. They need time on task. And trying to eliminate some of the pitfalls of wasted time is something I do. Okay. So they figure out the deflection function, and they can see that it has a minimum, and that minimum becomes important later. But the minimum is essentially telling them where the rainbow angle is. And you can see it's slightly shifted, ever so slightly shifted for different wavelengths. And they can do this. Actually, this particular function right here that I'm showing is the second rainbow. This is the double rainbow angle that's actually being shown, not the first one. And so you can ask the question, where's the double rainbow? And you can also figure out why it is reversed as well. Okay, so here's the advanced part. Why is the rainbow bright? You can actually figure out by basically accumulating intensity into different detector bins at different angles, if you like, and simply ask, what happens to all the intensity if I assume it has a little bit of breadth to it, if the rays aren't mathematical rays, but actually a little bit angularly broadened. And you basically set up simulated detectors and just keep accumulating intensity as you go ahead and let rays enter all parts of the raindrop. And sure enough, you see the rainbow angles emerge with these intensity maxima very clearly over the background, so to speak. And so this answers the question why the rainbow is bright. Okay, so in doing all of this stuff, and I'm sorry there's no animation or anything. Actually, I've tried to work on GlowScript to actually show basically a manipulatable ray, but that's, my GlowScript programming isn't quite so good with sliders and so forth, but someday. Be that as it may, the students develop these different skills of translating a model into code, debugging code, choosing scales, testing and validating code, making sure that the deflection is what they think it is. And really, the extraction of the physical insight is the other thing, a computational skill, if you will, computational physics skill. And that's basically asking, what do these graphs actually mean, okay? And so where, in fact, is the rainbow? Why is it? Why are the color order what it is? And why are rainbows bright? And so we eventually get to that. Okay, so that's what the rainbow exercise set is all about. It's fairly simple, okay, and hits on these different skills. And so now the question is, how do I deploy it? Because actually, it's quite a lot, especially if you were to do the last part. Okay. So context is all here. So this is how I use it. And again, keep in mind that we have our students taking these two computational physics courses. They don't necessarily take Physics 380 before they take intermediate optics, which I happen to be teaching this semester. So you still have people who are still pretty fresh to Python, say. So the way I implement this, yes?
Is 380 the computational physics course?
Yes, 380 is the computational physics course. That's the 3-credit-hour course.
And when do they normally take it, or is there no normal?
There is no normal. Basically, the only thing, because we have a lot of transfer students, it's hard for us to impose absolute sequence. And so what we end up doing is simply saying, you must take it before you take the capstone course for our major. So they can take it sort of anywhere up to the semester before their last semester. So I compensate for that by using the very first lab meeting of my intermediate optics course, and I hijack it for computational physics. And we actually do some of the plotting in the rainbow exercise set with a little bit of help, a scaffold or template, if you will, where I give them a template which allows them to plot a function. And so they figure out, oh, instead of figuring out all the overhead involved with plotting, they're figuring out the overhead of what's the function in the paper, and I can just translate that into the scaffold and then get going. And the paper also includes not only the functional form, but also experimental data points as well. So they get to reproduce a figure from a published paper. And so I hope that's a little bit powerful for them to do that. So I hijack part of a lab, part of that first lab in order to do that. Part of a homework assignment is figuring out the deflection function and plotting the deflection function. And that's actually pretty manageable. Because by the time they get the homework, they have actually done plotting in Python. So they know they just have to figure out what the function really is. Okay. And then in my intermediate optics course, I also deploy what are called challenge problems, where the students have to write some code. They start with templates often, but not always. And then they have to make a 5-minute presentation where they show the results and very efficiently cover the background of the problem, the solution to the problem, and the results showing the solution. And for the challenge problems, I have the rainbow intensity problem that I've shown in the exercise set. But in addition to that, when we cover the Fresnel coefficients for the different polarizations of light, I can actually have them calculate the rainbow polarization, because rainbows, it turns out, are really strongly polarized and tangential to the bow. And so they can actually show that this is so by actually throwing in Fresnel coefficient calculations together with the rainbow calculation. So that's how I put it all together in the context of my intermediate optics course. And so you can see, here's an example from a lab handout. Task number 3 is all about plotting the refractive index of water. Here's the homework problem. Actually, the plotting the refractive index of air has been thrown to homework. And then the other homework problem is the deflection function. And if you're interested in like getting the actual handouts, just send me an email. My email's at the end of the slides, and I'm happy to send you the stuff. And then challenge problems. Okay, and so really just writing it right on up, just like that. And so in the end, recognize the background and ability of your students when setting these tasks, and provide scaffolds, which for me take the form of code templates. And what I think is also really important is live coaching, which I think Walter basically does by having the Slack channel. That's an example to me of, if not exactly live, pretty darn close to live coaching. And so they really do need that kind of coaching. I had a student today coming in working on a challenge problem. He was so close to it, but he was getting very frustrated, and he just needed me to just do one correction and he was done. So that's the kind of thing, is that they really do need that. And finally, you can divide a fairly sizable exercise set into achievable chunks in different venues of your course, different parts of your course. So that's it. I mean, I could show you, plotting a plot, but that's really just not as exciting as looking at Walter's strings. At any rate, that's mostly it. And if there's any questions, I'm happy to take them.
Ernie, I have a question. It's been a long time since but what I thought I remembered was that if you have a functional form of the dispersion, if you have an actual dispersion function, then in closed form, you can show where the rainbow angle and the double bow angle are. Is that true or not? I may be misremembering. Because if so,
that's effectively true. I think it's basically all folded into their calculation of the deflection function. It's the ratio of the two indices matter, right?
Right. So they'll get it, of course, and it's in their data that they get from the papers. But my question is, if you had I thought you could do sort of a generic dispersion function. That you, in closed form, you would get the effectively the results that you have your students getting from dispersion data. Isn't that true? I'm remembering my basic optics.
You know, I have to say that I don't remember seeing a closed form expression for the rainbow.
Well, not quite closed form. I mean, you get a closed form expression for it, and then, but to actually, I mean, it's something in terms of a sine theta or what have you, and then, but to get what theta is, it's a nonlinear equation you'd have to solve anyway numerically. But I was wondering if that is true, and I may be misremembering, maybe it would be valuable to have them take a generic function, solve that nonlinear equation for theta, and compare it to the actual result using that are taken from data that your students do to see how it compares.
Yeah,
I may be misremembering the closed form expression part, but I that's what I remember.
I would be happy to talk with you about that because I don't actually remember seeing such an expression.
Okay, I could be totally wrong, but if so, it might be a little bit like what Walter did when he talks about his numerical results in terms of the small angle approximation result plus perturbation. It's not perturbation, but in a way, you're doing the same sort of comparison, if it's possible. And I may be totally misremembering. I'll have to go reread my Hecht to be sure. But this is beautiful. I like it. It's fantastic.
Okay, so I'm seeing on the chat, can we talk a little bit about the type of assessment that I do? So at what level do your students turn things in? Do you grade the challenge problems? You bet. The grade is essentially the results. If they don't have any result, that's not good for their grade. And usually they are talking with me quite a lot, so failure usually does not occur because they know they have to do something significant. And so they're usually in my office. As far as other assessment, it's pretty easy actually. So for example, when we get started with just doing plots, either their plot looks just like the figure in the paper or it doesn't. And so it's pretty much all or nothing. And they pretty much get it because the scaffolding gets them a good part of the way, and then they realize, okay, I just have to input the data or input the function and make just some small changes. And because after all, one of the points of this chat was that this is not a computational physics course or even a course about learning to program. It's a physics course, it's an optics course. So I don't want them to spend so much time learning to program as I do learning to extract optical information and using it, like almost immediately. I hope that answered the question about assessment. Yeah.
So I'll just add on, one of the things I really liked is that it wasn't you gave this to them and there was one grade at the end, right? There was this sort of progression of things that, they got a grade on the plotting, and then they got a grade on the homework problem, and then they got a grade on the second homework problem. So there was kind of a lead up to it. That's one of the things that I've run into in courses where I try to deploy something like this is if it's all at the end, the students get frustrated somewhere in the programming, and then the grade sort of hits them like a freight train at the end.
Yeah, I think that they get sort of this instantaneous feedback of, yeah, I got a plot. and now they can recycle this code, right? And so they sort of get into a good spot while being coached live.
Really what this conversation is about the value of formative assessment, right? That
Yes, that's right. Thank you for making that point, Walter. That's very concise. Good.
So
I'm sorry that it's 9 o'clock.
I'm sorry. That's my fault. You can hit me with pool noodles next time you see me.
we're very upset.
Can we pick up branded pool noodles?
Do they make those?
Bernie can find them for us.
So I think we should probably leave it there. We were hoping the presentations were both great. Thank you very much to Walter and Ernie. I think what we may do is try to save some of the discussion that we wanted to have for the next meeting, which will come up in a few weeks. If you have questions, I'm sure Walter or Ernie would be happy to respond to them at another time. You can either catch them on the Slack channel or just harass them with emails or hit them with pool noodles. And we'll stop there. So let's thank Walter and Ernie, and I'll shut down the recording and we can call this a night.
All right. Thanks a bunch, guys. Very well
Thanks
done.
for organizing, Nick.
Yep. Thank you.
Thank you.
Thank you all.
Thanks all.
Thank you.
Fantastic.
Thanks, everyone.